All right, guys, so let's continue. So we are at the point where we've been implementing, this is part B, right? Part two of implementing our model. So we are doing a regression model in Torch. We read the data with pandas, very powerful tool. We've got our pandas data frame there. We can view it. We got the list of it, and we can select which variables we want. So for instance, here I selected just fewer. Then we do some data as you start doing your data science, right? And that means understanding the variables, right? And so we did this code here to be able to print out a correlation matrix. And that's the correlation matrix. And we explained how it works in the previous video. All right, and then we converted the pandas data frame into a NumPy array. We printed it just to kind of view it. We printed the shapes, which is really important. And then you guys should become experts in indexing and slicing, as I've said, right? So this is something that you learn to appreciate over time. And so we did that, and we were able to take our NumPy and create X and Y. Then, of course, because it's machine learning, we need to do have train and test sets so that we can measure the performance of our model. This is what, if you're selling this model to someone, they'll want to know how good it is, right? And so you need to perform this task. Created a random seed every time you run your code. It's a different one. And this creates the 4 data sets, X train, Y train, X test, Y test. We printed out the shapes. You should always double check. And we printed out the data type. It was float 64. So we made a correction just in case Torch is going to give us an error later. So here's the code, just make it float 32. And then finally, we converted everything from NumPy into Torch. So these are actually Torch tensors at this time. So if we did something like Y test TR, right, it should say that it's a tensor. So we've got our Torch tensor in. All right, so now the next step is, I'm going to give it a heading, actually, because this is really important. But we're not going to do it now. Instead, we will come back to it. And sometimes this can make a huge difference, okay? Huge difference in the performance. And you might know where I'm going with this because I say it all the time. I mean normalization, right? Or scaling. This is really important. So normalization is the term that everybody uses. Okay. Now, there are 2 types of normalization, actually, because this is really called scaling. There's one called normalization, and then there's one called standardization. Okay. And I, in general, do standardization. I kind of like to do that. And so I'm just going to leave that in here as the 2 options that you should look at. So, and they're very simple to do. They're just 2 equations, basically, that we can actually implement those from scratch. So I'm just going to say normalization is 1. And at some point, we will take a look at the equation and standard. Okay, so we've got our 2 methodologies. This is usually the one that like I'll implement, basically. All right, but I'm not going to do it now because I want to show the results without it, and then later we can come back to it, okay? So that is performed, but that is performed basically. We're going to have X train TR, and then we're going to standardize it, and now we're going to have X train TR scale, okay? Now we can scale both the X's and the Y's. It just depends on the type of problem that we have, okay? So these are decisions that you can make as we got to think about it and what we want to do. Keep in mind, though, that if you do scale the Y's, then you have to descale them. Do you see what I'm saying? Because it would have no meaning if you just predict scaled y's, right? Whereas with the x's, it doesn't really matter because they come in, but then they can go into the model scaled. You're not going to get x's out of the model, but you do get y's out of the model, right? So just keep that in. And that's very straightforward to do, but we will explore it. All right, so anyway, I'm going to leave this kind of blank for now, the normalization part. And we will come back to it, as I said. So now all that remains is to create here it is. All right, so the next part that we need to create after scaling is, I'm just going to call this, I honestly don't have a great name for this, so I'm just going to call it what it usually is, which is create the data loader. Okay, so create the data loader. So what is this, you might ask? So all of this goes into the section that I had mentioned before called data wrangling. What we've been doing since we got that pandas data frame until now is we've been wrangling the data because it can get very difficult to process, right? This is easy compared to when we have natural language processing, you know, text, or we have images or something like that. It becomes much more difficult, and that's much more involved. Now, we could do all of this from scratch, but thankfully we have these objects like we have a couple of functions called tensor dataset and the data loader from Torch. All right, and they're very powerful things, objects that allow us to add the data into them, and then they'll do things like shuffle the data. They'll create the batches for us so that we don't have to slice things out of the data into batches, for instance. You see what I'm saying? Like we could, you know, do like indexing, right? We start at 0 and then 0 plus the batch size, and we slice that out. Then we iterate to the next one, and it's going to be a new index plus the batch, and they slice that out. We could do that manually, but we don't have to by just creating a data loader very conveniently. Okay, got it? All right, so that's what we're going to do now. And then the data loader really becomes the object that we're going to use, where our data lives in the future. Okay, we're going to do this just for the train set for now, and we're not going to do it for the test set. All right, we're going to need 2 new objects. Am I recording? Yeah, it's recording. All right, so create data loader, so we can hit run here. Okay, we're going to need 2 objects. So we need to get those, import those basically. Okay, so let's go to the top, and here, let's do from torch dot utils dot data import tensor dataset. Notice it's spelling capital T, capital D, and also data loader. And the L should be capitalized. Okay, so we're going to need these 2 from Torch. Okay, and that will very quickly create a data loader for us from our X train data and our Y train. So let's go ahead and run it, see if it gives us an error. Okay, so it worked. Now let's scroll down again to create data loader here. So now we can just add in our function. All right, so we're going to create an object called train DS for data sets. So let's call it train underscore ds. That's our data set, and it's an object using the function tensor data set. Okay, just like that. And this will take xtrain tr, right? That was our torch. And also y train tr. Got it? If we do the scaling later, we may need to change this, okay? Unless we use the same variable name. But remember, these are our x train and our y train. They go together. They were of sizes 3, 9, 1, 8, right? So that's the number of rows. So that's it. We just add these two items. Let's run that. Okay, no errors. And now to create the data loader, we're going to use train ds. Okay, so we can create a variable. This will be a very important variable called train dl for data loader. We invoke data loader like that. Yep. And we provide to it train ds, which is what we just created in the previous cell. And now we can specify some parameters. The parameters that we want are batch size, which we need to think of the batch size for this. And that will be so, I mean, the batch size usually, I guess the rule of thumb, it's small. It's actually not that big. 64 might be too big sometimes if you have a lot of data, especially if you have images. 64 images at a time when they're 300 by 300 RGB, that can get big. Okay, so don't think that a batch has to be like 2000 or something. They're small usually. A good practice is actually make them as small as possible and then increment them over time, you know, because otherwise you're gonna, as things get bigger with Torch, you start running out of memory and things like that. Okay, so watch. So, but for this, let's say 16. Now, we probably do not want to do this, okay, because this is a parameter that is going to be changing quite a bit. So it's a good time right now to introduce a section up here called parameters, okay? And these are the things that you're going to be manipulating as you do your problems, okay? So you want to have them in one easy area where you can modify them. Parameters, like the learning rate also should be here, okay? Things like that. Okay, so parameters. So I'm just going to say batch size. And since we're going to need the learning rate in a second, I'm just going to like do that now. So learning rate, I'm going to start with 0.001, and then we can change it. These are things that you can play with. Okay, so we've got a batch size of 16 and a learning rate of 0.001. Okay, so data loader, the second parameter is the batch size. Okay, so let's run this one. Okay, so batch size variable has now been created, so we can scroll down and just say here batch. Like that. Make sense? The last thing we want to do is a parameter called shuffle. So we're going to say shuffle equal true. True. What is this? Do you remember when we did the Celsius to Fahrenheit example? Do you guys remember that? In the Celsius to Fahrenheit example, we had 11 samples. And if you remember, we would always, every epoch, we gave it all 11, but we would, they always had the same order. Do you remember that? So it was always like the 11 as they were, 11, 11, 11. In machine learning, when you give the data to the model, you kind of don't always want to give it in the same way. So you shuffle it. But when you shuffle the X's, you shuffle the Y's so that you maintain that correlation, right? You don't want to break that. And this takes care of that without you having to do any coding. If you had to do that manually, it's a bit of coding, right? So it's nice. These 2 lines of code could be manually like 20 lines of code, right? So it's kind of very handy to do. Got it? All right, so you could do all of that manually, but I mean, at this point, just do it. So if you notice, the shuffling will be done. We don't have to worry about it. We gave it X train and Y train into DS. DS gets assigned here. We also specify that whenever we read from train DL, we're going to read in batches of 16. So what that means is we're going to have a for loop for, batch in data loader. And every time we grab a batch, it'll be a batch of 16 and they're going to be shuffled and so on. Got it? So all that will be done for us. All right, the last thing, that's it. I mean, the last thing we can do is just print train DL to kind of view it. So let's go ahead and hit go here, hit run, hit that works. Train DL now works, and this should be an object, a data loader object. So let's go ahead and print that one. Train underscore DL. So if I hit run, yeah. So it gives me the data loader object, and that's it, right? So we are ready now to start thinking about the model itself. Now comes the interesting part, right? So if you remember, in the previous example, I said we had the inference function, the loss function, and the loop, correct? That's what we did. And then the evaluation. So that's what we're about to start now. We are done with the data wrangling when we get to train DL. All right, so we are there. So to build a model here, and these are the steps. So since those are the sections, let's call it main loop and NN architectures. How about that? So let's do main loop for the loop, right? The training loop actually is probably a better name. Training loop, and I'm going to change this to NN, or for neural network. Architectures. Okay, just like that. So here I'm going to define the neural network architectures, and that's going to take several cells. And then here I'm going to do the train loop. Okay, and that's going to take several cells. Okay, so I'll probably begin with the training loop and then work my way back to the architectures. Okay, we're going to build several architectures that are going to be interchangeable, right? And you'll be able to run any one and see which one produces the best result. Okay, so the architectures we're going to build are a linear regression. So just linear regression, non-linear, right? So linear regression. Then we're going to build a multi-layer perceptron, right? Which is non-linear neural network. And then we're going to build a deep neural network, which you'll see the difference, right? So a deep neural network is a multi-layer perceptron with more layers, basically. So we're going to build those 3. We're also going to build a model that is a combination of a linear plus a non-linear model, right? So we're going to play with that. All right, so, but before we build the architectures, let's talk about the loop, right? So the loop that we want to do here. Now, remember, in the previous example, we only had epochs, but now we have batches, right? So we are going to then need to have 2 for loops, okay? So I had talked about this before. So let's go ahead and start building this approach. So Yeah, in the training loop, so this section here will be the loop function, so that we're gonna call yeah, so just training loop maybe. Loop. Define. Right, so this is going to be our function, right? The training loop, just like we did in a previous example. And then down here, we are going to initialize everything and invoke this function, okay? So let's start there. First thing we do is we're going to create the model. The model is going to be object-oriented. So what that means is we're going to define the model in a class, and then down here, we're going to instantiate that class, and that's the model, okay? And we're going to have several classes. And this is the standard approach nowadays to develop neural networks like in PyTorch, right? So you'll see this a lot, whether it's a transformer or a regression, we're taking this approach. So for instance, I will start with a very basic one, which is going to be called linear regression, okay? So that will be the first class, linear regression. So lin regression net. I'm giving it any name that I want because I'm going to define this class. And this class is going to inherit the NN module, basically, from PyTorch, okay? But this is what I'm building. So this is going to be the linear regression. I'll start there. Okay. And it'll take maybe some parameters. Okay. If we need to provide parameters. Okay, so and that should be it. Okay, so that's the instantiation of the class. So now, just to kind of illustrate, let's go back to neural network architectures and let's just create at least the class name for it. Okay, so here I'm going to say linear regression, right? And I'm going to say class lin regression net. You guys see that? That's basically what we're doing. Open parentheses, close parentheses, colon. Now, this is really important, okay? Inside here, I'm always going to say NN dot module. So what is NN module? NN module is like a generic class in Torch itself to build neural network modules, okay? So we're doing class inheritance here. Do you see what I'm saying? So you may remember that concept in your programming at some point where you had a class and another class, and then one class inherits the other class. That's what we're doing. Okay, so it's class inheritance. All right, but anyway, you know, it's gonna be pretty straightforward. So we just do this for all our modules, right? So lin reg net is the name we give it, and we need to inherit NN module. Got it? All right, and then after that, we're gonna create some main functions. So for now, I'm just going to provide a comment, okay? I'm gonna say something like initialize, so init the class, like the constructor and all that stuff. So init the class, all right? Okay, so let's leave it there for now. So notice we need to build the architectures. Okay, this will be our standard approach. We're gonna need to build a training loop, and then down here is where we bring everything together, right? We instantiate the model. Now, another thing we should probably look at is I use something called nn.module, right, in the class, nn. So we need to bring that into the space of our code. So we're going to go up to our up here, and we can say import. So notice that I am now importing specific things from Torch itself, right? So I've already done this once when I imported Optim in the previous example. Now we're importing the NN modules class, and also we're going to import one more thing called functional. So these are the three things that will allow us to build our neural networks. So let's do import torch dot NN as NN, okay? And we're also going to do, since we're here already, import torch dot NN dot functional as F, okay? And Optim was something we had already done before, so you're familiar with that one. So we're just going to do it again. Import torch dot Optim as Optim. Okay, so let's run these three because they're essential to what we're going to do. Okay, no errors. So now let's go back down. So we've got our model there. You guys have any questions? Questions? All right, so we've got our model there. Now, what do we need to do? We need to, if you remember, I said that in machine learning, we have an inference function, a loss function, and we have the training loop, right? Do you remember that? So do we have an inference function so far? No? Model is your inference function. So I think we had used the word model before, I want to say, right? So that's why it's always going, this is your model. So actually this will take your X's and give you your Y's. Do you guys see that? That's your inference function. If it's a GPT, like ChatGPT, it's going to say something like transformer something GPT, but we're going to call it model. We're going to give it a sentence. It's going to give us another sentence. Do you see what I'm saying? So I'm showing this line is what we're going to, how we're going to write our code now and at the end of the semester. It's not going to change. Okay. Got it? All right. Very important. So we did that part. What was the other part? We had the loss function. We also defined the optimizer, right? Do you guys remember that? Those two are related. So for the loss function, before I had to write a whole bunch of equations, and if you remember, a whole bunch of things. However, when you're writing your models, it's probably not a good idea to have to write all those equations unless you're doing research. Like if you're doing research and you need to get in there, you know, and modify things, okay, then you write the equations. But otherwise, just use the built-in losses. So if you remember in the example of Celsius to Fahrenheit, we called the loss function loss Fn. Do you guys remember that? And then it was equal to all the equations. Now we're just going to use conveniently the functional that we just imported, f, and we're going to say f dot MSE underscore loss. And that's it. Okay, that's it. That's the same MSE that we did before, right? So that's the same y minus y hat squared, the sum of that, the means. It's the same one, just instead of writing all of that, we just use the torch built-in function. And that's usually the better approach. Any questions on that one? All right, and then the next thing we want to do is we want to do the optimizer. Okay, in this case, I'm going to call it opt. And this is going to be equal to, I know I called it optim, but I'm just going to use it like this. Torch dot optim. And if you remember before, what did we use? SGD, right? Stochastic gradient descent. So we've seen how that one works. You can try it if you want, but in this case, I'm going to use Atom. The Atom optimizer is just like stochastic gradient descent, but with optimizations, okay? All right. So if you guys look at, maybe you can go back to the code that we wrote for the Celsius and Fahrenheit. can you guys tell me what the parameters were for this optimizer? For the SGD optimizer, what were the parameters? Was it batch size? No, in like, no, right, you're saying the parameters that we created, but my question is, in the Celsius and Fahrenheit code, right, we also initialized optim as a stochastic gradient descent optimizer, and it had some arguments in here. What I mean is, what went in here for that one? The params, right? And what were params? In square brackets, right? But what was in it? Yeah, and what did it represent? What did param? Huh? The W and the, well, yeah, M is W, yes. The W and the B, the weight and the bias, right? Do you guys remember that? And you remember that the weights and the bias are for the equation Y equals W times X plus B. So we got the X that gives us the Y, and we have to learn the W and the B, correct? Those parameters. So we explicitly created a tensor of those variables in the previous example. We could still do that. However, the NN module that we're using provides an alternative, which is a little bit more efficient. So model is the inference function. So it's equivalent to say that this is Y equals W times X plus B. Do you see that? Somehow that's in there already. So model already has that in, and so we can just access it from it instead of creating a separate variable. And the way to do that is to type model dot parameters. Do you guys see that? Does that make sense? When we start to, because remember that before we built the equation from scratch, but this time around, linregnet, right, will be this class, and we're gonna build everything in there, but using nn.module, okay? So the way that that works is that the parameters, the weights and the biases are gonna be in there already, okay? And we can just access them if we need to. You'll see how we constructed when we get to it. Got it? All right, but I'm just trying to tie it right now. All right, so instead of params, it's still the parameters, but we just get them from the model itself, the nn.module. All right, so hopefully that made sense. And then the other thing is, of course, the learning rate. So to do that one, we're just going to do LR equal, and we already created a variable, right? Learning rate. And I put it at the top so that it's something easy that can be easily changed. Currently 0.01. No, 0.001. All right, so that's it. And then the next thing that we do in here is to invoke training loop. So training loop then is your function, right? It's gonna have some parameters. We need to provide n epochs. That's something that we define, right? N epochs. So we probably should define this at the top as well. So let's go to the top. And let's define n epochs. And I don't know what this can be. I'm trying to think for the wine data. Probably 1,000 epochs, something like that. So remember, epochs is the number of times that you give the whole data set. So all 4,000 or so samples to the, so we're going to give all 4,000 training samples to the model about 1,000 times. But every time we're reading now in batches of 16 and we're shuffling, right? Remember, that's why we created the train DL object. So hit run here. Right. And we are here, right? So we're adding the parameters to the training loop. So we've got n epochs. We also need to provide the model. So that's model, comma. We also need to provide the loss fn function, loss fn, and what else? and we need to provide the optimizer op. You guys see that? Any questions? All right, so obviously now we need to go ahead and define train loop. Okay, so we're gonna move up here a little bit. Those are the arguments. So we need to look at this. So it takes number of epochs, the model, loss of n, and opt. And now we're ready to create the two for loops, right? So the first one is for epochs. So we can just say for epoch in range and epochs, right? Okay, so we're going to do this for loop. Remember, this is just showing the data to the model that many times, all the data. Second for loop is for the batches, because we're going to read in the data in batches. Now, because we created train DL, that should be pretty convenient to do. So the way that we do it is for XB, comma, YB in what? Train DL. Remember train DL? Train DL is this one, right? Remember? So you made it batch size 16, shuffle, all that stuff. So this has the train data. And so conveniently, we can just say for XB, YB in train DL. And that gives us the X samples, the Y samples, and that's pretty, that helps us out a lot, right? To do our, again, you could do this from scratch, but it's just, much more work. Okay, so you guys should know the rest. So I can probably just like sit down at this point and so, because we did it, right? For the Celsius to Fahrenheit, we did this already. So what did we do? Yes. Then what? Through the loss, right? Then what? Right? Which was how? The three things, right? What were they? Zero out the gradients. Loss dot backward. Steps. See, you already know how to do it. That's it. That's what you have to do. So let's do it then. Y hat, let's just call it Y pred. Yeah, let's call it Y pred. So Y pred is basically the result of calling model, and model needs to take an input. Yeah, so the input is going to be what? What's the input to model? Here, think of model as your Y equals W times X plus B, right? So what goes into model? X, right? In this case, XB. Do you see that? XB just means X batch, the Y batch, okay? And that gives you Y pred. So now you calculate the loss. Now remember, I already did a discussion where this part is where we create the computational graph in memory. So we're building all of that. Remember also that when we created params, we said gradient train equal true. Remember that? But we don't have to do that here because we will be using the NN module. So that, gives us a lot of those things. Okay, but it's available if we want to switch it on and off. Okay. All right. So loss here will be equal to the loss function, right? Which we pass here, loss Fn. And if you remember, loss Fn is just f dot MSE loss, right? That's it. Yeah. Okay. So loss here then is loss Fn, right? All right. Now this function needs to take two parameters. What are they? Right. So Y pred, comma, YB, right? That's it. All right. So we've got our loss. And basically we've got our computational graph in memory. And now we just do those 3 steps to do the calculate the derivatives and take a step. All right, so let's do the first one, opt dot zero grad, right? So we're going to zero out every iteration, the gradients, the zero grad. We do that. Then the next step is loss dot backward. Think of it as going into the computational graph and calculating the derivatives. So the plus, the sign, right? Plus or minus. And then finally update the weights, the parameters. So we're going to do opt dot step like that. Got it? Remember, we tied opt with the model by doing this, right? So they are tied together. Got it? Any questions? All right, then other things you can do, you might want, as you're training, you may want to print the loss. Remember, we were doing that. We were printing the loss. But because you're going to be maybe doing more iterations, sometimes it's a good idea not to print every single loss, but only every few losses. So we can do that more easily by having an if statement. So we can say if epoch modulus 200 equals 0, then print the loss. So you can say something like epoch, comma, loss, comma, and the actual loss. Do you see that? So what happens here is basically, long story short, every 200, it's going to print the loss. You can, if you want every 100, change this to 100. If you want every 20, change that to 20. This is just a modulus operation. It's a math operation of the remainders. Okay, got it? All right, good. So that's a way of printing the loss. We also want to create chart like we did, I think, in the previous one. We want to create little graphs of the losses so that we can view how it's learning and everything. So I encourage you to create a list for that. What else? Just keep in mind, actually, yeah, that's an important thing to think about here. How are we going to approach this? I mean, how do I put this? So right now, this will train the model. This will train the model, and it'll print the losses. What I was thinking about is that you also want to start thinking about printing out a metric, right? And there's a metric for regression, which is called the R-squared. Okay, so for classification, you know, you may have, maybe if you've taken a machine learning class before, you did something like what? Precision, recall, F measure. That's classification. But that's when you're predicting if it's a cat or dog or something like that. In our case, we are predicting what? Real valued numbers, right? We're predicting a quality score like 3, 5, 7, something like that. So and that's a regression problem, and it's got its own metric called the R-squared. Okay. So the R-squared is I'm going to calculate that one with something from sklearn, which means I'm going to use NumPy. But our results are all torch. Yeah. Everything that we're doing is torch. So we're going to need to do something we did before, which is to take a torch value and detach it, right? And then make it into a NumPy. Got it? I think we've done this before. So we're going to do that again for the R-squared. So how do we proceed? Let's see. We do have let's not do that for now. Let's just do it like this, okay? I think if we just, yeah, this should be enough. So let's just try to run this model because I don't want to add too much complexity yet. So instead, this should be complete, the training loop, and we're going to print the loss. So we'll have that. So for this code to run, the only thing that's missing is for us to define the model itself, Lin regression net. So I want to do that first and then run the code, and then we're going to start adding complexity to this, okay? So this function should be done. So I'm going to hit, yeah, no errors. This will error out because I haven't defined Lin regression net yet. So then let's go here and define Lin regression net. Okay. All right. So as I said, to kind of go back to this idea, right? The last part of this, in order for it to run, we are basically building a class, right? Our own Python class. We're calling it Lin regression net, but we're going to use class inheritance. So what that means is that this class will get a whole bunch of functions and variables and things from another class, right? And that's the generic nn.module class from Torch. Okay, so that's what we're going to do. So long story short, this class inherits a lot of things, and all we need to do is define a couple of things, which are the initialization function and then a function called forward. Okay, we need to have a function called forward, which actually performs the inference. So in one, we define things, and in the other one, we build the architecture with those things and perform the prediction. Okay, so to do that, we need these two functions, and we're, for the most part, always going to have these functions. So pay attention here. It should be two underscores, 1, 2, init, like that, okay? So you need to do that. And then because it's a class, this function needs to have the word self here, comma, and then whatever, if we provide any parameters, they would go in here. However, for us, for our case, we're not providing anything yet. But just be aware, if we had any variables that we want to pass, we would pass them there. Okay. So just do that. Colon. All right. And then I'm going to add just a pound sign here for now, and we'll come back to it. The second function, I will give it comment. I'll say perform inference. Okay. And this is going to be the function called forward that you need to define with that name. So define forward, open parentheses, close parentheses. This one will take at least two parameters. One is the self because it's a class, and the other one is x. Because remember, you're giving it x, and it's going to predict y, right? So it takes that. Got it, guys? Okay. So now let's go to init first. All right. And in here, we need to now start defining things. The first thing we do is we do super dot 2 underscores init. Oh, not like that. 2 underscores parentheses. What is this? This is the initialization function of the class that you're inheriting. Okay, that's why we do that. So when we do this, we initialize all that stuff in NN module, and we're good. That's it. Okay, and now we have it available, and all we need to do is define our interior stuff. Okay, so I'll start with linear regression because that's the simplest thing. And actually, I think it only takes one line of code. All right, so we need to go in after super, and we're going to invoke self, right? Because this is a class, right? Self. And we're going to create a variable called linear 1. Linear 1. And linear 1 is going to be equal to nn dot linear. Okay? Huh? Oh, I'm sorry. Yeah, sorry. Thank you. Do you see that, guys? Is this making sense? Once you see a lot of examples of this, it'll click even more, okay? But basically, we're defining the architecture here. A linear, if I say linear, so for a neural network to be nonlinear, it needs to have multiple layers, and the layers need to go through something called activation functions. These are all math things that we need to look at some point in the slides, okay? And we'll do examples of all of that. But if we don't have activation functions and we only have one layer, it's basically a nonlinear model. Is this clear? So all we need to define here then, and this is the inputs and the outputs. Okay, so let me, this is a moment, I forgot that this part required me to draw the network. I can do that really quickly. Okay, so this part means we are now defining neural network architectures. Okay. Okay, so we're gonna go to the whiteboard. And think about what that means. Okay. So I wrote that function self dot linear one, right? Linear one equals, I think it was linear. No, nn dot linear, right? Yeah, nn dot linear. It was nn dot linear. And then like that. Okay. We're gonna start building neural networks with this, like Legos, basically. So for instance, in a neural network that has more layers, then I would do self linear 2, yeah. And then it would also be an NN linear, because NN linear is the thing in Torch, right, that allows you to define, and then you just give a different name. And then we would start building the network. Do you guys see that? So that's kind of where we're going. But in this example, I only have one line of code. So what that implies, and there's also NN dot activations like sigmoid, etc., that we would bring in. But for now, we're not doing any of that. So neural networks usually are like, you have this, right? This is how the block, right? A layer of a certain number of neurons connected to another layer of a certain number of neurons. Do you see that? That's usually what we're doing. So this is done with these functions. So all we have to do is put a comma here, and then we indicate the number of neurons in this layer and the number of neurons in that layer. That's it. Do you see that? And that basically is what we're doing. So our equation actually looks like wx plus b, right? Where these are actually vectors of size 11, right? So these are of size 11. So it's almost in a way like saying x1 w1 plus x2 w2 plus x3 w3 dot 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 x11 w11. Do you guys see that? So that's kind of the equation that we are writing out. To tie this back to the first equation that we did for the Celsius to Fahrenheit, which was really just equivalent to something like this. There's also a B down. Okay, do you guys see that? So this is what we did with Celsius to Fahrenheit. Oops. This is what we're doing now. Okay, but we don't have to write out these equations. Instead, we just use this notation like this. And all we have to do is indicate the number of inputs and the number of outputs. And if it's linear or non-linear. So if it was, for instance, non-linear, this would be y hat, right, yeah, like that. And then we can say this is y f final. And then this would be sigmoid of y hat. Do you see that? So this function would go into, or sorry, this y would go into another function and then would come out as the final value. Do you see that? That's called an activation. We will do that, but just not right now. Okay. So right now, I'm not doing this part either. We'll get into those functions later as well. So we are only doing this, but in Torch, we write it out like that. Okay, so now what does NN linear really look like? So let's do a new one. So self dot linear one is NN dot linear. Okay, when we start writing code like this, we call it that we're building the architecture of our neural networks. So it's a good idea to start drawing these out, like on your notebook. Oh, this is too small. It's a good idea to start drawing this out in like your notebooks or something. So this is one layer, and this is another layer. In our case, this model only has two layers, which are the input and the output, and nothing else. There's nothing in between. Do you guys see that? How many outputs does the model have? How many values? I don't see. I haven't put, okay, all right. Good. All right. No, you're right. Yeah, so following my logic, the output is this value here, a number, the number of things we're predicting, right? And this is the number of inputs to the model. So this is dependent on the data. So X and Y. So X was how many rows and how many columns? And the columns? 11, right? So every sample had 11 columns, correct? Yeah. So every sample that we give to our model will be a vector of size 11. Okay. So 11. There's 11 neurons. 5, 6, 7, 8, 9, 10, 11. Literally, that means there's 11 neurons in the neural network. The first 11 neurons in the neural network. So that's 11. You see that because the data set X train is something like 3,900 something by 11. So that value is what goes here. Okay, the value of each vector. What about the Y vector? That was 3,900 something, 1, right? So that value is what goes there. So then it is 1. So then, oops, this layer has how many neurons? 1. Very good. Do you guys see that? That's it. That's your first, it's a neural network. It's just a neural network that's linear with no activations, but this is a neural network. Okay. All right. So that's it. We built our first neural network, and that's as we start creating other neural networks, we're going to come back to this idea of drawing the diagram, and then you'll see, oh yeah, that's why they're called neural nets. Okay. Now you assume that this is fully connected. That's the last thing I'll say. What that means is that there's a connection between every neuron in one layer and the neurons in the other, if you say it's fully connected. Now, you could make things that are not fully connected, but you need additional code for that. See, it's a neural network.
So is each one of the self-linears its own neural network?
Say that again?
Is each one of our self-linears one neural network?
This is a whole neural network.
Okay.
Each one of these, I guess you could call it a neuron.
Yeah.
Like this is a neuron connected to that neuron. Like in the brain. So the idea is in the brain, you have a neuron here and a neuron here and a thing that connects them. It's the same idea. Yeah, but this is the very basic one. This is just linear, no activation, no other hidden layers. Okay, everyone with me? Questions? This is important, although we will do many of these. But I mean, all semester we're doing this. All right, great. So now that you understand this concept, then we can go back to finishing out the code. So let's share the screen. And so now we can go back in here and just type in 11, 1. Do you guys see that? This is very dependent on the data itself. Now, this only defines the neurons, if you will, that we're going to use, but we haven't connected it yet, right? So we need to tie it to the X data, which is the input. So we do that below. So notice that it's linear. That's the generic object in an N, and linear 1 is the variable. So linear 1 is the thing that we reference, okay? It's the thing that we're going to use. So I'm going to go down here, and now I'm going to say what? I'm going to say y pred equals, y pred is equal to what? Self, right? Because it's a class. Dot what? Which one? Linear 1, yeah. You're right. And this is the point in which we give it the X. The input goes in here. Okay, that's something that is handled by nn.module, but all we need to do is plug it in there, right? And then pass it over here. And then when we have another layer, what's going to happen is we're going to have like, you know, we're just going to pass y pred, for instance, to the next one. Yeah. Yes, exactly right. Or instead, if you have multiple layers, you can just get in, you know, call it X and just overwrite that variable. But for now, let's just do this. So y pred. Okay. And that's pretty much it. Once we do this, all we have to do is return. Y pred. So if I didn't make any mistakes, I think this will run. That's it. All right, so let's go ahead and run it. See if it errors out. And if it doesn't, we should see at least the loss function going down, okay? We are doing 1,000 epochs, so that will print 5 losses. So let me I want to print more. So let me go to, let's do 20. All right, so I'm going to go ahead and I think it was all good up to here. I'm going to hit run. Run. We didn't normalize it yet. Create a DS, DL, print a DL. Now we're going to load our architecture. See this is done now. So there we go. No errors. Skip all of that. Define the training loop. All right, this is the critical part, right? Let's see if it crashes. It works. Nice. So let's look at that loss function, right? So it's look at the dot, right? It's training. Now this training is now it's training a neural network, right? The loss went from 9 to 0.56, so far so good. And this is going to run for 1,000 epochs, right? So it's quite a bit that it's going to print. So it's a 57. That's it. Any questions? 47, so it's going down. And that's yeah. That's it. Our goal, of course, is to get really good predictions. So we're going to need to add things like performance metrics and such things. Okay. Actually, it went to 1.21 there, so you can see that it's having trouble. Let's see if it goes down again. I mean, we're only at 100 iterations, but at this point, I can't really tell you what else to do, except what was the key thing? Normalize, right? You want to normalize the data, change the learning rate, give it more epochs, you know, and of course, change the architecture. We're building a linear model. It could be that the relationship between the 11 features and the quality is nonlinear. So we need nonlinear models. I don't know. Okay, it went back again. Now we're at the lowest ever, 39. So that's good. Right? And that's kind of it. This is the game that we're going to be playing all semester. Any questions, guys? Okay. Huh? Go to the neural network architecture? Sure. There you go. And I'll be posting this code on GitHub soon. Remember, this is just a linear model, okay? But we're using the same approach that we would take to build any kind of neural network, including a deep neural network. Has anyone, I know my computer's a bit slow, so are you guys ahead of me? You are? And is the loss kind of just stuck there in the 30s? Hmm? 380? This one is, my lowest is 0.36, I think. 0.2069. Okay, that's lower. Okay, 800. Okay. Yeah, maybe I did too many iterations. Did you put, and did it finish already? Lenny? Did it finish if you put 200? Or is it still going?
It's still going.
Okay. Yeah, so that's kind of it. Yeah. Go ahead. Yeah, where? The for loop? Yeah. Mm-hmm.
Okay, now it's getting.
Mm-hmm. Yeah.
Like delve into my laptop is super slow.
Repeat the question. What's the question?
Will we learn how to like integrate this and use it on our actual like GPU?
You want to use it on the GPU?
Well, not right now. Like, will we learn how to do that before we have to like do this on our own? Or could I come to office?
Yeah, no, I'm thinking how to, give me a second, I'm processing it. How could you integrate this into the CUDA? So if you have to have a torch for CUDA first. So you got to go through the installation, which is not difficult for torch. You have to know, I guess you're telling me that your laptop, your GPU on your laptop supports CUDA. You got to check that, right? Okay, perfect. So if you do that, then what you should do is follow the instructions to install Torch for CUDA. Then there are commands that you can run to check that it is actually using CUDA. And then what you do is there's a couple of places where you have to say, load this to CUDA. And that's it. The code in general does not change. You guys see that? So there's only a couple of places. So I don't have a GPU here, but I'll look into you know, what places you would specify use CUDA. But it's not, like I said, it's not a lot that changes. So yes, to answer your question, yes, we can do. Not today.
Yes.
All right, okay, we were waiting for this to finish. So minus, yeah, it's kind of stuck at 0.56. You know, what I would say is normalization, more neural, you know. All right, so I think this is a good stopping point for today. All right, we finished and we've built our first linear model using the torch approach, right? And then modules next time around, next week, next Wednesday, I'm going to just continue. So we're going to add multi-layer perceptron, deep neural networks, all that. We're going to normalize the data. And we need to add the metric R squared, which is called the coefficient of determination. And also we're going to run the model on the test set. Okay, so basically we're just going to start to now measure performance of our model. Got it, guys? All right, so yeah, so this is a good stopping point. Let's just let it run. I'm going to stop the video here. It's kind of here at 0.55. It's at 720 iterations. Oh, you're done with it? What was your loss? 0.4. Yeah, and the 4-ish, it's kind of where it is now. And so I don't know what the result will be, but you have to get, you know, we're going to start testing it in the next class. Okay. Okay, guys. All right. Yeah. So we'll, I'll stop the video and we'll just continue here.